This is the lesson for the EP2 assignment on momentum and impulse. When I was a kid, I remember stepping off the boat onto the dock, and I thought to myself, I can make that gap. So when I stepped, I fell in the water. Because when I stepped forward, the boat moved the opposite direction. And this brings about Newton's third law of motion. For every action, there is an equal and opposite reaction. We're going to start by looking at the formulas in this unit. The momentum of an object depends on two things: how fast it is traveling and its mass. The larger the mass, or the faster an object is moving, the more momentum that object has. Momentum is symbolized by a capital P, and it is expressed in units of kilogram meters per second. The total initial momentum is equal to the total final momentum. The sum of the momentum of all things moving at the beginning will equal the sum of all the momentum of all the things moving after the event. The total momentum is the addition of the individual momentum of all moving objects. This could be equal to 0 if nothing is moving, or it could be the sum of several moving objects. When an object undergoes a change in momentum, it is due to a change in that object's velocity. As earlier stated, a change in velocity occurs when a force is applied. The change in velocity of the object will depend on the magnitude of the force and how long that force is applied to the object. This product is referred to as impulse, symbolized by a capital J, and it is expressed in units of Newton seconds. J is thought of as a shove. The shove, how hard that shove is, how much of a change in momentum you have will depend on two factors: how hard you are pushed, which is the force, and for how long you've been pushed, which is the time. Whoa, check out this ramp. Now I'm going to roll a ball down this ramp. And remember that objects, regardless of their horizontal speed, take the same amount of time to fall to the ground if they fall from the same height and have the same initial vertical speed. So the distance objects travel over the time period will give us their velocities relative to one another. So I recorded the track twice. The first time with nothing in the path of the marble that will be rolling down the ramp. But on the right-hand side, the second time I ran it, I put a marble in the path of the marble that will be rolling down the ramp. That means we will have a collision. Now, as the marbles travel down, I, through the magic of PowerPoint, have put X's to show you where the marbles made contact with the ground. This will help show us the relative velocities of the marble when it rolled down the ramp without a collision and the velocities of the two marbles when there was a collision. So we'll draw some velocity vectors. There we go, the one that did not have itself involved in a collision. Then we had the one that had been hit by the marble and the one that rolled down the ramp and lost velocity because it had hit the marble that was in its way. Now, if I take the two and put them together, the velocity vectors are equal to one another, which means the momentum before equals the momentum after the collision. Whoa, there's a marble sitting on the floor. I wonder what could happen. Woo, that was a good time. Now let's run that again, except this time I'm going to draw the path that the marbles follow. That looks pretty good. Okay, this time I'm going to draw X's at certain time intervals. Click, click, click. There we go. So there we go. Equal time intervals so that we can tell what the relative velocities are of, well, the ball that's coming in and the relative velocities of the balls after the collision. So let's do that again and draw some velocity vectors. So if I take the velocity vectors of the marbles after the collisions and put them together, tail to tip, they are equal to the velocity vector of the marble that was coming in. So that means momentum has been conserved in both the x-axis as well as the y-axis. Here I have a cannonball sitting in a cannon. My initial momentum total is equal to 0 because nothing is moving. When the cannon is fired, the cannon moves in the negative direction and the ball moves in the positive direction. So the total final momentum is equal to the momentum of the cannon plus the momentum of the ball when the ball is leaving the cannon. The mass of cannon, velocity of cannon is in the negative direction, and the mass of ball, velocity of ball, is in the positive direction, and they are equal and opposite. The ball was traveling faster than the cannon, but the cannon weighs more than the ball. So the total final momentum is also equal to 0, which means total momentum initial equals total momentum final. Now on ships, when they'd shoot off a cannon to ensure that nobody was injured, they often would chain the cannon to the side of the boat. So when the cannon's momentum carried it backwards, no one was injured. In Quebec City, if you've ever taken the tour of the old part of Quebec City, you will see that the cannons were put on rails that went uphill. So when the cannon was shot, that momentum, which gave it kinetic energy, was transferred to potential energy. That potential energy back to kinetic energy as it would roll back down to its original position. Now let's say I've got a giant paintball that is inside of the cannon. The initial momentum will be the ball flying towards me. And I got hit with the ball and I was wearing butter shoes and I kept going. The total initial momentum equals the total final momentum. Initially moving was just the paintball. At the end, it was me and the paintball combined. Mass times the velocity of the ball was in the positive direction, and that equaled the mass of me and the ball together multiplied by the velocity of me and the ball together in the positive direction. The ball was initially traveling faster. After it hit me, our combined masses then traveled slower, but the product of both sides are equal to each other. Now let's say I got that same paintball, but instead of breaking open, it hits me and bounces off. Again, the total momentum at the beginning equals the total momentum at the end. Initially, it's just the paintball coming in. At the end, it's the paintball that's moving as well as myself. Initially, the paintball was going in the positive direction. Afterwards, I was going in the positive direction, but the paintball was going in the negative direction. So that means my velocity had to be even greater. I received an impulse. I received a shove when the ball hit me. I also received the shove of the ball leaving in the opposite direction. In university, I went and talked to one of the teacher assistants and I said, how do I know when I'm doing questions whether or not I should be using kinetic energy, potential energy to solve for it, or whether I should be using momentum to solve for the question? And they told me, you'll know. And I said, no, I don't know, and that's why I'm here. And they were like, oh no, you'll know. Well, this might help you out. Momentum questions are those where objects either collide and bounce off one another, collide and merge into one final object, or separate from one object into two or more pieces. Example 1. What is the momentum of a 725 kilogram car traveling 100 kilometers an hour? So I'm asked, what is the momentum? We're given a mass of 725 kilograms, and we're told the velocity is 100 kilometers per hour, which will have to be converted to meters per second. We said the magic number is 3.6. Meters per second is always smaller, so velocity is 27.7 repeating meters per second. Momentum equals mass times velocity. I can sub in mass and velocity, and that gives me 20,139 kilogram meters per second, which corrected to three significant figures is 20,100 kilometer meter per second. Example 2. A constant force is applied to a 2,500 kilogram snowmobile for 60.0 seconds. If the snowmobile's initial velocity is 6.00 meters per second north, and the final velocity is 28.0 meters per second north, what is the change in the snowmobile's momentum? We're given a mass of 2,500 kilograms, time is 60.0 seconds, initial velocity is 6.00 meters per second north, final velocity is 28.0 meters per second north, and we're asked, what is the change in the snowmobile's momentum? So I'm looking for delta P. Delta P equals mass times change in velocity. Change is always final subtract initial. So for delta V, I will sub in VF subtract VI. I can now put my numbers into the equation. First, I'll do what's inside the brackets. 28.0 subtract 6.00 gives me 22.0. And then I multiply it by the mass of 2,500 kilograms. And the change in momentum equals 55,000 kilogram meters per second. Part B. What is the net force acting on the snowmobile? So I'm looking for force now. Impulse equals change in momentum. Impulse also equals force multiplied by time. So I will sub in force multiplied by time for impulse. I want to solve for force. So to get force by itself, I will divide both sides by time. So time on the left-hand side will factor out. And I have isolated force. It is equal to change in momentum divided by time. I will sub in the change in momentum that I found in part A and divide it by the time of 60.0 seconds. So the average force acting on the snowmobile over this time period is 916.6 repeating kilogram meters per second squared, which will be written as 920 newtons. Example 3. An object experiences an impulse of 637.5 newton seconds south. What would be the change in velocity if the object weighs 5.0 kilograms? So impulse, which is J, is equal to 637.5 newton seconds south. We're looking for the change in velocity, so delta V is our unknown, and the mass is 5.0 kilograms. Impulse equals change in momentum, and change in momentum is equal to mass multiplied by change in velocity. So I will sub in mass delta V for delta P. I want to get delta V by itself, so I will divide both sides by mass. The masses on the right-hand side factor out. Delta V has been isolated, and it's equal to impulse divided by mass. Now I can sub my numbers in. 637.5 newton seconds divided by 5.0 kilograms gives me, corrected to the correct number of significant figures, 130 meters per second south. Now part B. What would be the change in velocity if the object is 10.0 kilograms, so double the mass? Our impulse is 637.5 newton seconds south. We're looking for that change in velocity, and we're told the mass is now 10.0 kilograms. We've already done the formula rearrangement. We know that delta V equals impulse divided by mass. So our impulse of 637.5 newton seconds south divided by 10 kilograms this time gives us a velocity of 63.8 meters per second south. Receiving the same shove, if the object weighed twice as much, its velocity would only change by half of what the 5 kilogram object did change by. If the 10.0 kilogram mass was initially moving 25.0 meters per second north and experienced the impulse, what would be its final momentum? So again, impulse is 637.5 Newton seconds south. Initial velocity, we've been given it as 25.0 meters per second north, which I wrote my variable list as negative 25.0 meters per second south because I want to make sure that all my directions are the same. So I'm going to put anything that has a direction, I will make it south in my variable list. Mass is 10.0 kilograms, and I'm looking for the final momentum. I know that change in momentum equals final momentum subtract initial momentum, because change is always final subtract initial. Initial momentum is going to equal mass times initial velocity. To get momentum final by itself, I will add mvi to both sides, so that on the right-hand side, mvi subtract mvi will cancel out, and I will have final momentum isolated, equal to change in momentum, which I know because it equals impulse, plus mass times initial velocity. So I will sub the numbers in, do the multiplication first, and then I do subtraction, and the final momentum is equal to 388 kilogram meters per second south. Example 4. I have a 135-gram rubber bullet traveling 47 meters per second, striking a 4.50 kilogram target. What is the final velocity of the target if the bullet becomes embedded in the target? So I'm told after they hit, the two become stuck together. Mass of bullet, I want it in kilograms, so 135 grams is 0.135 kilograms. Velocity of the bullet, initially traveling 47 meters per second. It hits a target. Its mass is 4.50 kilograms. Velocity of the bullet and target at the end is what I'm looking for. So how fast are the bullet and target moving once the bullet has become embedded in the target? Mass of bullet and target together are going to equal 4.635 kilograms. That's mass of bullet and mass of target added together. And the velocity of the target initially is 0 meters per second. So I'm starting with total momentum initial equals total momentum final. Initially, I have the bullet moving and I have the target. In the end, I have just one object. So I chose the subscript BT for the final, that's bullet and target together, and B and T separated for bullet and target initially. Initially, the target is not moving, so it does not have momentum. That means the momentum of the bullet at the beginning will equal the momentum of the bullet and target once it has merged. Momentum equals mass times velocity, so momentum of the bullet equals mass bullet times velocity bullet, and momentum of the bullet in the target equals the mass of the bullet in the target multiplied by velocity of the bullet in the target. I'm looking for velocity of bullet target, so I divide both sides by MPT. Now I can sub my numbers in, and that gives me 1.37 meters per second. Part B, what is the final velocity of the bullet if the target is traveling 2.70 meters per second after the bullet has hit the target? So now I've got a situation where I have a bullet at the beginning and a bullet by itself at the end. I have a target at the beginning and I have a target by itself at the end. So I'm going to have bullet initial, bullet final, target initial, and target final in my variable list. So mass of bullet is 0.135 kilograms. Now I didn't write initial or final with mass of bullet because the mass of the bullet is the same in both situations. Velocity of the bullet, it is initially traveling 47 meters per second. Mass of target, the target before and after does not change its mass, it is 4.50 kilograms. Velocity of the bullet at the end, we do not know. Velocity of the target, initially, the target is not moving, but we know that the target after it has been hit is traveling 2.70 meters per second. So I'm going to start with total momentum of everything initially will equal the total momentum of everything at the end. Initially moving, I have the bullet and I have the target. At the end, I have the bullet and the target. Now, initially, we said the target is not moving. So again, that can be eliminated. So that means the momentum of the bullet at the beginning will equal the sum of the momentum of the bullet at the end to the momentum of the target at the end. So I'm going to sub in mass times velocity for each of these momentums. I'm looking for velocity of the bullet at the end. So first I will subtract mTVTF from both sides. And now I have MB equals MB subtract MT And to get VBF by itself, I will now divide both sides by MB. So MB on the right-hand side will factor out, and velocity bullet final will have been isolated. So now I will sub my numbers in. I'll do the multiplication first on the top. That way I keep track of my significant figures. I'll do the subtraction in the numerator now. Go to one decimal place, go to one decimal place. So subtraction of those numbers means that the numerators go to one decimal place. And then 2 significant figures divided by 3 significant figures gives me 2 significant figures as an answer. I get negative 43 meters per second. So that tells me the bullet hit the target and then bounced back and is traveling in the opposite direction from which it came. And that's it. You're going to work on the EP2 assignment. Hopefully you can self-motivate. You don't need a little bit of a shove. And once you start going, you're going to find that once you got a little bit of momentum, it's going to carry you through the rest of the assignment. But make sure you stick with it. Get it done. Because if you don't, you're going to feel like you're drowning.